Okay, questions about anything else from last class? All right. So we'll jump in to, we'll clean up what we talked about at the end of last class, which was Tor. And then I'm going to show you, we'll switch gears to a different kind of topic. Okay, so we had this like relatively complicated protocol. If you break it down step by step, it's not complicated. It's more that it's long and it's kind of doing a nested version of what it was doing in the first three steps, the next three steps, and the next three steps. But essentially, we have Alice, we have a server, a Tor server, and what she's going to do is do a TLS style handshake. Sorry, she has a TLS link. She's going to do a handshake between her and N1 and get a session key between her and N1. Then what she's going to do is she's going to do a handshake for N2, but she's going to encrypt it using the information that she derived from the handshake for N1. Then she'll repeat the process. She'll do a handshake with N3. She'll send it through N2, and she's reaching N2 through N1. And she's going to have an encrypted channel from her to N1, from her to N2, and then when she does the handshake, she'll have it between her and N3. Okay? And so when she's ready to send data, this is what it looks like. I did change this slightly, so it's a little different from what you wrote down. The thing that changed is the CIDs. I kind of moved them outside of the encryption itself. So this is on the this is what's on Moodle is this corrected version. But if you were taking notes last class, your notes will be slightly wrong. Or if you watch the video, you'll notice that I write it in a different order than it is now. But this is the right order. Okay, so basically what happens is, let's just walk through this because I was trying to write it out quickly, and then we'll walk through it, the intuition of it. Yeah.
Oh, I gotta walk through it?
Yeah, yeah.
Okay, so I'm asked, like, so you don't encrypt the CID anymore?
Yeah, exactly. Yeah, yeah. So we'll see why that's the case. Okay, so Alice sends to N1 this payload. So there's an encryption under K1, which she shares with N1. And now the CID is outside of the encryption, okay? Why did I move it outside the encryption? Well, when node 1 receives this packet, it needs to know basically, it needs to know which connection this is, okay? It has no idea. Now, because Alice is probably unique, it's not like Alice has multiple connections to N1. It can probably tell just by Alice's IP address or something like that. Like it would have ways of maybe keeping track of it. But the CID is informative. And later when we see CID2 and CID3, it'll be clearer why it needs to be outside. But anyways, so once it has CDI1, then it can go look up in its log and it can say, okay, this is circuit ID 1. Things are encrypted with K1. Okay, so now it's able to decrypt this packet. Before it knows CDI1, it doesn't know how to decrypt this packet. So before, when CDI1 was inside, it has K1, but it also has keys for everyone else that's talking to it on Tor. And so it would need to find the right key. Yeah. So it might keep track of the problem is it's sort of like, I wrote that it's talking to Alice, but it's not clear what that means. Like, who is Alice? Like, is Alice an IP address? That's fine. But let's say Alice changes her IP address. Now N1 gets completely lost, right? It doesn't know that this is Alice anymore because it wrote down the IP address. So it will never find the right key to decrypt it, and then the packet will just drop. So to keep it so that it's more reliable, it doesn't really have to track who Alice is. We just use the CDID1, and then it's very clear and unambiguous.
So if it changes to those, it just needs to know who's talking to who, doesn't know who Alice is.
Exactly. It doesn't know who Alice is. It knows that this is the key I'm sharing with this user. Yeah. And then everything I receive, I need to send on to N2. And I'm going to mark it with CDID2. Does that make sense?
Yeah.
Okay. All right. So then what happens is it decrypts this. So it grabs this inside bit. Okay. Now, technically, because CDID1 is here, you maybe don't strictly need CDID2. We could have the node put that in, okay? Because the node has it in its database. Here it knows CDID2, but Alice also knows it, so she might as well put it in and just save the trouble for the node, okay? So it will look it up. It can look up CDID2, and it knows that that's going to N2. Okay, so CDID1, by looking this up, it gets two pieces of information. One is it knows the next place it needs to send it. So it knows that it now has to send it to N2. And it gets the decryption key so that it can pull this payload out. Okay, so then it just copies and pastes this payload. It sends it to N2, and N2 receives it. Okay, N2 is going to do the exact same thing. It's going to look at CDID2. All right. When it looks at CDID2, it will go through its logs and it will say, okay, I have a log CDID2. I did receive it from N1, and K2 is the key that I need to use to decrypt it. And when I'm done with it, I'm going to send it on to N3. Okay. So from CDID2, I got the identity of N3. So that's where I'm going to send the next message. And I got the decryption key K2. And so now I'm able to decrypt this packet. Okay. Now, it's really important that CID2 is outside of the encryption. It's more important than with Alice because Alice is kind of unique. Like, she has an IP address and things like that. But because these are both Tor nodes, there might be a lot of traffic from N1 to N2. So just because N2 sees traffic that came from N1, it does not tell it that it's this particular connection, okay? It might have 100 or 1,000 connections between N1 and N2, all right? So it really needs this to make sure that it has the right connection, the right circuit. All right, so then it knows it's sending to N3. It has the decryption key, so it decrypts it, and then it drops it onto the web. Sorry, it drops it to N3. N3 will use ID3. It will get its K3. So it has ID3 and it has K3. And then it's going to look at the packet, and the packet's going to tell it where to go. Okay, so the packet could be an HTTP request to a website. Then it will go to that website and it will send that request. It might be HTTPS as well. Okay, if it's HTTPS, it's the same thing. On the outside of the packet is where it's going to the server, otherwise it wouldn't be able to route it. So it just sends it to the server itself, and then it waits for a response from the server. Okay, if it's over HTTP, what that means is that between N3 and the website, there's no encryption. Okay, so N3 can see the content. It knows what website is being visited, and it can see the content of that website itself. Okay, if it's HTTPS, then there is encryption on this last link, and importantly, that encryption is between Alice and the server itself. Okay, so Alice has an end-to-end encrypted channel. It's not a link encryption just between N3 and the server. Like N3 and the server do a handshake and now they have an encrypted channel. It's an end-to-end encryption where Alice has an end-to-end encryption to the server. Okay, so N3 cannot do anything in the middle. It's a man in the middle now, but it can't decrypt any of the information or inspect any of the information at all. Okay, so this could be end-to-end encrypted. That's what ETEE means, end-to-end encrypted, between Alice and the web. N3 is just a hop that's on the path between Alice and the web. Or if there's no encryption, decryption, sorry, if there's no encryption, no HTTPS, just HTTP, then any N3 can read it, anyone between N3 and the website obviously can read it in both cases. Okay, does that make sense? Okay, so Tor and HTTPS are doing two different things. You would want both from a security perspective. Tor is hiding your IP address, and HTTPS is keeping your traffic confidential from any man in the middle, plus integrity on it as well.
So packet sniffing on Tor, somebody's using Tor, which will work the same way. You're still going to see packets going. And is there going to be more encryption or harder to decipher what's going on?
So if N3 runs a packet sniffer on the outbound traffic, yeah?
Yeah. Well, let's say Alice's method.
On Alice's circuit?
Yeah.
Well, first off, it can't, okay. I guess, okay, so it can do it. It doesn't know who Alice is, but it can run it on everything marked with CID3. So that would be everything that belongs to one particular user. Sure. Yeah, so in this case, it would just be like a normal man in the middle. Like Alice's ISP would see the same information. Alice's Wi-Fi router would see the same information. So what it sees would depend if it's encrypted or not. But it's going to see all the packets. They just might be encrypted packets or unencrypted packets. Yeah. Other questions about this? Okay. Then on the way back, what happens? So on the way back, the website will respond. N3 needs a way to keep track of, because maybe it has two users that are going through it, they're both going to Google. So it's going to have to be able to track which goes to Google. Google doesn't know anything about Tor, so it can't use a custom protocol in order to do that. So it would have to keep track of, probably at the TCP level, there's some identifiers on packets and things like that. I'm not actually exactly sure how it does it, but it would have to probably record that so that when the responses come back, it knows that it's came from circuit ID 3 as opposed to any other circuit it has between it and the website. So what it's going to do is it's going to say, okay, I know what this is. I know that this belongs to CD ID 3. And so it's going to go into its log. It's going to pull out the ID, CID3. It's going to pull out K3. It's going to encrypt the response with K3. And then what it's going to do is it needs to send it to N2. Okay, so N3 will send it to N2. All right. N2 will receive it. So this is what N2 sees. N2 will look at CD ID 3. It will say, okay, I need to send this to N1 using K2, and I'm going to mark it with CD ID 2. Okay, so it encrypts it with K2, it marks it with CID 2, and it sends it to N1. Okay, so all three of those pieces of information it got from CD ID 3. Then node 1 receives it. So node 1 sees this. Okay, so node 1 can't decrypt this at all. It has no idea. It doesn't have K2. All it sees is CD ID 2. So node 1 will go into its database and say, okay, I have a record for CIDD2. Okay, it's coming from N2, which is where it came from. What I need to do is I need to send it to Alice, and I'm going to use CID1 to mark it, and I'm going to encrypt it with K1. So it marks it with CID1, encrypts it with K1, and then sends it to Alice. And then Alice can decrypt these three layers of encryption and just get the response from the website as if it was delivered directly to her from the website itself. Again, that response could be HTTPS encrypted, or it could be just HTTP. Okay, questions about how this all works? Okay, and the security property we want is, so two things. One is that no node should know anything beyond its neighbor nodes. So let's look at N2, because N2 is probably the logical one. So N2 on the path forward from Alice forward, okay? All it sees is an encryption of something, okay? And it has CID2, and when it decrypts it, it sees CID3, okay? So it knows CID2, it knows CID3. It does not have K3, so it can't decrypt any further into this packet, okay? So the only thing it learns is 2 CIDs, and that's exactly what's in its log anyways. Okay, so CID2 and CID3 is what's in its log. So it's not learning anything beyond what's in its log. And what's in its log is I'm getting traffic from N1 and I'm sending it to N3. N2 knows N1 and it knows N3, but N2 doesn't know anything about Alice, and N2 doesn't know anything about the server itself. Okay, all it knows is it's relaying traffic between N1 and N2 and N3. And then similarly, when we build in the responses, what N2 receives again is a CID3, okay, and it can't decrypt this. Okay, this is encrypted with K3, so all it knows is this one CID3. That's all it knows. Okay, so then the only thing it can infer is whatever is in its log about CID3, which is the same information that we just covered. Okay, so that's the only thing that we need. Okay, questions about that? So what doesn't it know? So it doesn't know Alice, it doesn't know server. It also doesn't know how long the chain is. Okay, it knows it's at least 3 nodes long because it's receiving it from another Tor node and it's sending it to another Tor node. But it could be 4 nodes long, it could be 5 nodes long. N3 knows it's dumping at a server and it's receiving it from another Tor node, but it doesn't know whether this is the first or the 5th node in the chain. So everyone just has a local view. They just know where they're getting it from, where they're sending it to, and that's the only thing that they know. The encryption, I didn't mention it. Basically, for the rest of this class, every time I write down encryption, I'm going to assume it's authenticated encryption. So that means CCA, secure. It means that it encrypts and it MACs, either all at once because you're using something like AES GCM, or it explicitly is doing an encrypt and MAC combination, a secure combination of the two, but we'll assume that as well. Okay, questions about Tor before we move on? Okay. Okay, we're going to stop talking about secure tunnels for a bit, although everything is kind of a tunnel in the end. But I'm going to switch gears. I want to talk about secure messaging. Yeah. So I'll talk about 2 protocols. The first one is something we all use every day, which is email. And the second is I want to talk about instant messaging protocols. And so the one I'll talk about is called Signal. And it's used inside of WhatsApp. So you can run Signal as its own app, or if you use WhatsApp, it's using the same cryptography. There are differences between the two, like the way it's implemented, and especially around meta information, so like who's talking to who and how much of that is known. But the core cryptography, the cryptography that we'll look at in this class is used both by WhatsApp and by Signal. Okay. The difference between these two is with Signal, it's more of an interactive protocol. Sorry, just give me 1 second. So it's an interactive protocol. It means, it doesn't strictly mean, it used to be the case that you would assume that if Alice is talking to Bob, they're both online. And if they're both online, they could do something like a crypto handshake. Okay, you could send a message 3 ways and then you could start doing stuff. Okay, now we have it designed so that Bob can be offline, at least initially, and you can still make progress. So you could send an offline message. But email is very, very like non-interactive. It's like I send you an email and you might not look at it for 3 days. Okay, so whatever crypto I'm going to do, I need to do it right now. Like I haven't talked to, and maybe I'm sending an email to you for the very first time. We've never talked before. So I'm going to try and do some crypto now, and that's it. I do it, I send the email, it's gone, all the crypto's done. Whereas instant messaging is a little more interactive, and so you can, you'll see you can do different things because it's interactive. These are also closed protocols, meaning everybody, like if I message another user on Signal, they're also using Signal. They have the same software installed and all that type of stuff. So if there's any changes I want to make to a protocol, I can make it to both ends, and then that's fine. Email's like an open protocol. So I can change how my email client works, but I can't change how your email client works. Okay, your email client might work completely different. Okay, so there's no like one company that's in charge of email. So email, you know, it goes, everyone, yeah, it needs to be client. Okay. Okay, so what I'm going to do is I'm going to actually start with Signal. It's kind of the, I don't know, maybe email's easier, like it's a less involved protocol, but email's really messy. Okay, so there actually isn't a good solution. You'll find that that's the main thing that we'll find, whereas Signal has an actual protocol itself. So we'll start with Signal. It's more structured, and then we'll talk about the sort of mess that is email after. Okay, so Signal uses a sub-protocol that we haven't looked at yet called a ratchet. So I'm going to describe what a ratchet is first, and then we'll look at how Signal uses it specifically. Yeah, so I mentioned the concept already, yeah. So, sorry, I mentioned it at a high level, yeah. In fact, actually, I guess I drew a picture out, so I take it back. You've all seen it before, but now we'll look at it in detail.
You put 2 keys together.
Exactly, yeah. Yeah, okay. Okay, so this is what a ratchet does. So you start with an initial key. Sorry, my kids are at home. I'm just trying to manage them. Okay, so this initial key, sometimes we call it a root key. I'll use that terminology. And the value that we get, I'll call it RK0, we get through doing Diffie-Hellman. So Alice and Bob just do Diffie-Hellman. They get a shared secret key. Okay, and so I'll put Diffie-Hellman. And they end up with a normal root key. Now, once you have that key, you can use it forever. Okay, so I have this key with you. We can use it forever. And what's the problem with using a key forever?
Reply attack.
Okay, so if someone steals it at some point, then it's not going to be useful. It's not going to give me any privacy going forward. And it may also not give me privacy going backwards in time as well. Okay, so the whole idea of a ratchet is we want to refresh our key. And we want to refresh it in a way so that if our key is compromised at some point, hopefully our past messages are secure still. And hopefully we have an ability to sort of recover in the future from it as well. Okay, so the way we ratchet is we do a new Diffie-Hellman. So this is Alice and Bob. I'm not writing out Diffie-Hellman. I assume that you know it by now because you've seen it so many times. But basically the shared secret that they get would be like G to the A0, B0. Okay. And what we're going to do is we're going to run it through a KDF. Remember, a KDF is roughly a PRG, so pseudo-random generator run on an extractor, run on whatever the input is. Okay, so the extractor just squishes it, makes it random, and the PRG expands it. So you can generate as many keys as you want from it. So you can generate 10 keys, you can generate 20 keys. Okay.
The KDF expanded, right?
Exactly, yeah. Yeah, so it sort of runs both of these.
What is ratchet specifically?
It just, let me draw a little more and then I'll show it. So, okay. So what we're going to do is we're going to update this root key. Okay. So I'm going to always have a root key and I'm going to remember it. That's kind of like my secret going forward. And then I'm going to get a second key because the KDF can generate more than one key. And this is the key I'm going to use. Okay, so I could use it to encrypt things, Mac things, whatever. There's whatever I'm doing. So in Signal, it would be like encrypting messages for other people. Okay, it'll be a little more complicated in Signal, but anyways. Okay, so this is the key I'm going to use. That's fine. Then I can just keep doing it. So anytime I get kind of worried about my key being compromised, I can generate a new one. Now, Alice or Bob will go first. So usually one of them initiates. It doesn't really matter which one initiates. Let's say that Alice initiates first. What Alice will do is she'll do the first half of Diffie-Hellman. So she'll have a new secret, but because Bob hasn't responded yet, Bob will still be on the old secret. And so we'll get a new K2, and Alice will use this. And I'll just note that this is what's changing. Okay, then on the next message, when Bob responds, Bob can include his new Diffie-Hellman. And so then we can update it like this. And this is the key, for example, that Bob will use. Okay, and we can keep doing that. And sometimes in Signal, basically every time you sort of, if I send you 5 messages in a row, I'll use the same key. But then when it's your turn to send me back a message, you'll update your Diffie-Hellman, and then we'll all switch our keys over. Okay, and then we'll sort of go back and forth. So every time I sort of send stuff to you, I'm switching my key and then you're switching it back.
Like here, there is three individuals or just two?
Sorry?
Three individuals
Yeah,
here?
there's just Alice.
Just two, sorry,
Because
just
the
Alice and
one
Bob.
the first key I will use.
Yeah, so that can be that Alice or Bob will use.
So every time they send a message, they get a new key.
So sort of, so
They get two new keys.
So I haven't mapped this onto Signal yet. So this is just a protocol where you can refresh your key. Let's just keep it at that for now. And then in Signal, I'll show you explicitly what message uses which key. Yeah. Okay. All right. So we have this ability to update keys, essentially. Okay. Now, what are the security properties here? First, I drew this wrong. All right, let's say the adversary is able to corrupt at this stage. So they're going to get, say, RK1, that should say RK2, sorry, and K2.
And that's RK3, that's the last one.
Yeah, thank you. Okay, so this is the adversary. Okay, so let's assume they compromise. It can be either or both. So I'll say and or K2. Okay, so now they know everything in green. Do they know K1? So K1 was the key that I was just using before we did the update.
No.
Okay, and why not?
Because it has, they have done the KDF, so you cannot actually extract K1.
Okay, so KDFs are one-way functions. So you can see the output of a KDF, you can't go back and get the input. Okay, so because it's one way, I can't go from here to here and get K1 back. Okay, so what that means is all the messages that use K1 are still secure, even if K2 is compromised. Okay. So we cannot learn K1 because PRG, well, KDF and PRGs is one way. So it's like a hash function in that sense. Okay, now let's do the same thing. Let's say I compromise RK2 and or K2. Will I learn what K3 is? Okay,
You
No.
can't.
if you're using KDF.
Okay, it's people who say can't, why not?
Because Bob has to generate his the Diffie element.
Yeah.
Okay. So I can run through the KDF forward. So if I have the input to the KDF, I can run it forward. But I'm missing the second input to the KDF. And specifically, I don't know what B1 is. Okay. And even if I'm on the wire, I see G to the A1, I see G to the B1, but I don't know G to the A1, B1. Okay, that's the Diffie-Hellman. So the Diffie-Hellman protects it. Okay. So if these two are compromised, I cannot learn K3 because I cannot learn G to the A1, B1. What if I can control, let's say, forget about the green square for a second. So pretend I don't know any of the keys. I don't know any of the RK1 or any of that stuff. But somehow I'm able to like corrupt the channel here. And so I can choose messages to feed into the KDF. So I just pick a message 10 or whatever, and I feed it into the KDF. Am I able to determine what K1 or RK1 is?
Because you cannot determine the function.
Okay, so if I don't know the initial root key, I'm mixing my randomness in with something that I don't know. So there's two inputs, one that I'm choosing, but the other one I don't know, and I'm not able to get the other input from just knowing one. It's actually the same thing here. So the reason I can't compromise it is if I know RK2, I know one of the two inputs, but I don't know the second input. So here it's like I know this input, but I don't know this input. Okay?
So if I know G to the power A1, and
Yeah.
I know G to the power B1,
Yeah.
can I know easily G to the power A1, B1?
You cannot, that's Diffie-Hellman.
So I can.
So how?
I don't know.
So think about it. Convince yourself. So I'm going to write this here. This is called the Diffie-Hellman problem or assumption. Sorry, so I'll write it as, so this is called computational Diffie-Hellman. Can you compute Diffie-Hellman is what it says.
Because of discrete law.
It's slightly, so let's come back to that in a second. So I know G to the A, and I know G to the B. My job is to output G to the AB. Okay. If I can break the discrete log, then I can get A out, and then I can take G to the B and raise it to the power of A. That will give me G to the AB. Okay. But short of that, what can I do? I can multiply these together, but then I'm going to get G to the A plus B, not G to the A. I can do G to the A raised to the power of G to the B, but then I'm going to get G to the A times G all to the B. Yeah? But there's no way to directly get G to the A times B. Yeah?
So how Diffie-Hellman works if I can't get G to the A, B?
So what I'm saying is somebody who sees these three values cannot get G to the AB. Okay? Who sees these three values? The person in the middle. Okay, so Alice and Bob are talking. I'm in the middle. I see these three values. I cannot compute this value. Okay? But Alice and Bob themselves,
No, A1 and B.
Alice knows A and Bob knows B.
Yeah.
Yeah, so Alice and Bob can compute G to the AB, right? Because Alice will take G to the B and raise it to A, and Bob will take G to the A and raise it to the B. So both Alice and Bob can compute G to the AB, but no one else on the planet. Even if they see everything that Alice and Bob are talking about, they can't compute G to the AB. Does that make sense?
Yeah.
Okay, so that is the Diffie-Hellman protocol, and it's like the original 1978 crypto protocol, 77, I think. Yeah, it kickstarted all of cryptography. And yeah, so 6110, you'll learn about it if you haven't already. Okay, but yeah, for this course, I just jumped in assuming that this would be something that we would already know. Okay, so back here, so if I can inject values for G to the A, I'll just put AI, BI, it doesn't really matter what stage. I cannot influence or learn any of the Ks that go along with it. Okay, so this, the idea that if I compromise, I can't rewind in time and decrypt past information, we call forward secrecy. So we've seen that concept before. Here, the idea that if I compromise, they can recover the conversation. We call it break-in recovery. And the last one is if I can't inject things, we just call it resilience. Okay, so this ratchet scheme is forward secret, it has break-in recovery, and it also has resilience, according to these definitions. Okay, questions about the ratchet? Okay. All right, then let's look at how Signal uses it. So Signal uses, they call it a double ratchet. When you look at it, you might think it's even a triple ratchet because there's kind of like 3 ratchets, but there's 2 kinds of ratchets, and then there's 3 sort of chains. So there's going to be a main chain, which is creating these sort of master secrets, and then there's going to be a chain for generating keys that Alice will use to send stuff to Bob. And there'll be a separate chain for Bob to send messages back to Alice. So just like in TLS, the messages, the keys that go in one direction for traffic in one direction are different from the keys that do traffic in the other direction. Okay, every user in Signal has a bunch of keys. Okay, they're going to have like a long-term key. So this is sort of like your permanent key. You generate it once. You might change it every time you reinstall Signal or something like that. Maybe every couple of years or something, but it's like your long-term key itself. Because I'm going to go offline at certain times and I still want to receive messages, the second thing I'll do is I'll generate like a key that's good for, I don't know what it is, like a day, let's say a day. And I'll generate a bunch of them. So I'll generate a key for today, tomorrow, for the next month maybe. And I'm going to upload them to a server, and Signal's going to keep those keys for me. And if any of you want to talk to me and I'm offline, you can ask the server for my key and it will give you that key. And then you can use it to kickstart a conversation, okay? So I'm going to call this, I'm going to just mark it with a tilde, and I'll call it an epoch key. So epoch is like a period of time. So this is your long-term key. This is an epoch key. And it's going to be stored on a server, on one of Signal's servers. And then as I'm doing conversations with everyone, I'm going to generate Diffie-Hellman keys, if you want to call them keys, or exponents. So when we start talking, I'll generate one for you, and then we're going to ratchet, so I'm going to keep updating it. But then I'll have another conversation with someone else. I'm going to have different keys for that as well, okay? So I'm just going to denote them with a subscript like A0, A1, A2, etc. And so these are my ephemeral keys. Or session keys. Okay, and no one knows these. They don't store them. I don't store them or anything like that. They're just random keys that I'm generating on the fly. I'll remember them for as long as our conversation, but then I'll delete them once we ratchet to a new key itself. Okay, Bob will have the same configuration, and all users will do the same thing. So Bob will have G to the B. He'll have his epoch key, and then he'll have his set of ephemeral keys. Okay, questions? All right, So what we're going to do is the first stage, we're going to have like a registration phase, I'll call it.
Further, sorry, further.
Yep.
maybe I wasn't paying attention. The ephemeral key goes on to how many? Because you wrote A1, A2.
So over time, you'll generate more and more. So as the longer you use it,
Conversation.
yep. So you'll generate one of these essentially. If I send you 10 messages, I generally won't generate 10 of them. I'll generate one for those 10 messages. But then once you respond, you'll generate a new one. And then when I respond to you again, then I'll generate a new one. So sort of every time the conversation sort of shifts, like there's a round trip, we generate a new ephemeral key. Yeah. So if we've been talking for 5 years, we're going to have millions, or I don't know how many, thousands of these keys or whatever.
Telegram work this way?
So it also uses encrypted communication. I don't know the.
Telegram actually uses MT Proto 2.0, so by default it uses that, but it has some secret chats, so that in the secret chats you can actually choose to use this protocol. By default it doesn't use it.
Okay.
You can choose it.
Okay. Good. Yeah. Okay. Okay. Registration. So because we're going to go offline sometimes, what we're going to do is we're going to have a server kind of help us out. If we're both online at the same time, we don't really need this step, but this is how it's going to work. So we're going to have a server. It should be untrusted, so it should work even if the server is malicious. We'll talk about that in a second. And so here's Alice, here's Bob. So what the user will send, what Alice will send, is they'll send who they are, so their identity. They'll send their long-term key. They'll send a epoch key, so like think of it as a daily key, okay? And they're going to sign the daily key with their long-term key just to prove that it's something that they are choosing for themselves, okay? And then Bob will do the same thing. All users will do the same thing. So in this notation, the subscript here just means that it's signing with B, G to the B. And in reality, what they'll do is they'll usually send a whole bunch of these at once. So they'll send a pool. So they'll say, here's a whole bunch of them. You have a bunch for the next month or whatever from me. And so the server will rotate through them. Yeah.
One question, why Alice signed the epoch key, not the long-term?
So she doesn't have a key to sign the long-term one with. She could self-sign it, but self-signing it doesn't really prove anything. So what she's doing here is she's kind of like making a chain where she's proving that if you somehow know her long-term secret, yeah, then you know this is the right ephemeral key for that long-term secret, okay? So ultimately what we'd like Alice to know is what Bob's long-term secret is. Because it's long-term, Alice can verify that once. And once it's verified, then doesn't have to change it. And then because this is changing every day, I have a way to make sure that the server's not lying to me and the server's not making up these ephemeral keys. Yeah. So it's a good question. Let me try and rephrase it slightly different. Let's say we ask the server for this information about Bob. I'm Alice. It basically can lie in one of two places. It can lie about the long-term key, or it can lie about the ephemeral key. Yeah. And so the long-term key, we need some way to verify that it's correct. Okay. If I can do that, then it can't lie to me about the short-term key anymore because it's got to be signed with the long-term key. It can only lie to me about the long-term key. Does that make sense? Yeah. Okay. So let's I'll write that down here. So server can lie about G to the B but not about g to the b prime. At least not without also lying about g to the b itself, okay, because of the signature. Okay. Any other questions about this enrollment? All right. So now Alice wants to send a message to Bob. So she's going to do kind of like a handshake, except for because Bob's offline, it's going to be like half of a handshake. The half that she can do without Bob replying. Later, when Bob comes online and sends a message back, then the handshake will sort of complete. But she'll send her sort of half of the handshake. Okay, so Alice will go to the server and say, I want to talk to Bob. Okay, so I don't know what that is. It could be an email address or a phone number or some unique identifier for Bob. And the server will say, okay, I know who Bob is. Bob uses WhatsApp or Signal. And so here's Bob's long-term secret. Here's Bob's latest epoch key. And here's a signature using the long-term secret on the epoch key. So that you know that the epoch key, I didn't just make it up. Okay? But I might have made up the long-term key, but I didn't make up the short-term key. Yeah.
Can you run out of epoch keys, or is it always going to generate new ones?
So because they need to be signed, Bob has to give them, the server can't generate it on your behalf. Yeah. So it has to be generated by Bob. So yeah, you can run out. So if you send 100 and it burns through them, then it's, yeah, you would have to reconnect to the server itself. I don't know how it fails in that case. It might just keep the last one alive until you reconnect, or maybe it does actually give an error message. I'm not sure how it handles that, but yeah. Okay. Okay, so I get back this package. Okay. Now what I'm going to do is I'm going to do a couple things with this packet. So the first thing I'm going to do is I'm going to check the signature. So I'll check that it's properly signed with G to the B. The second thing is I need to check that G to the B is right, that is actually Bob's public key. Okay. How do I do that? Does anyone know? Okay, so there could be some sort of certificate thing, but in that case, what that means is every user who uses this would have to get certified. If you've ever signed up for these things, you know that you don't have to get a certificate or anything like that.
I mean, you have fetched one of Bob's, like, one of the keys from his bundle, right? So can you use that?
So I have a key that the server told me is from Bob's bundle, but
You have to
how do I know that that's Bob's? So how do I know the server isn't lying to me about what Bob's key is?
Signature.
So the signature is on the ephemeral key, but I don't have a signature on B here. And if I did have a signature, then it's like, well, who's signing that? And so it becomes a certificate really fast. Like as soon as you're like, well, Signal's signing it or
So
whatever.
if you sign it, it will become a certificate.
Yeah, then it becomes a certificate. And then whoever signed it is now the trusted party. So that would be one architecture. So that's, remember, we call this PKI. How do you know a key belongs to whoever? So in HTTPS, we use certificates and certificate authorities. So that's one PKI. Here we're using a different PKI. So we could just trust the server. So that's another kind of PKI. We call it a directory. So you just have a key directory. The server knows everyone's key, and it's trusted. But here we're going to do something else. Well, in addition to that, if you trust the server, you don't have to do anything.
You might have a root directory for those.
So you could have a root that, again, that would tie it to a certificate authority. What would be in the root would be the authorities, but we don't have an authority in this case.
So it's in the end it's a PKI, right?
Yeah, in the end, we need a PKI solution here. Yeah. Okay, so the way we do it is the way you're supposed to do it. How many people actually do it? I don't know, but we call it out of band. Out of band, and that's kind of a weird sounding term, but it just means that you sort of do it in real life. Okay, so if you open up a conversation with anyone in Signal and you go into the settings, there'll be something called, I forget the term they use, I wrote it down, a safety number. So I'll try and show you what it looks like, although it won't be in the video itself. So let's say you're not going to see it very well, but I'll just sort of show it to you. So I have a colleague, Fenwick McKelvey. He's on Signal with me. And so I clicked on his name, and there's a bunch of options here. And one of them says view safety number. And so when I do it, I get a QR code, and I get like some codes itself.
This is in WhatsApp?
Pardon?
WhatsApp?
This is Signal, but WhatsApp will be similar, I think. I don't use WhatsApp, but I assume it's similar. Yeah. And so there's a bunch of numbers, and there's a QR code. Okay. And so what I can do is, if we're in the same room, he can scan my QR code, I can scan his, and we can compare them. If we're talking over the phone or something like that. Now, again, if there's an adversary in the middle using machine learning, it could maybe simulate my voice and change the numbers that I'm saying. But assuming that I have a secure, conversation with him and nobody's interfering with it, then I can read out my numbers, he can read out his. And the point is that our numbers should match. So when he looks at his screen and I look at my screen, we should have the same set of numbers.
And this is outbound, right?
And so we call it out of band because it's not happening in Signal. It's relying on us seeing it in real life, doing a video call, reading it over the phone, that type of thing. Yeah. So we call that out of band in general. Yeah. Okay. So what is the safety number itself? Well, I said that both of us see the same thing. So what it is, it's going to be a blend of my long-term key with his long-term key. Okay. So so out of band, we have a safety number. And so what the safety number is going to be is it's going to effectively be G to the A, B. So that's my long-term key. So I'll have a different safety number with every one of my contacts, and you'll have a different safety number with all of his contacts, okay? So this is Alice's long-term secret, and this is Bob's. And because they're long-term, the safety number, as long as Alice and Bob are talking, the safety number is not going to change. It's going to be the same for the next 3 years or whatever, as long as they keep their long-term secret, okay? Now, this number is kind of big. It's kind of like too big to fit into a QR code. So what they'll do is they'll truncate it. So I'll just write trunk. So you sort of hash it and then you truncate it. Truncating meaning you just take the first whatever. They take a big chunk of it, but not like the entire thing itself. And it's basically secure as long as the adversary couldn't pick a different B such that G to the AB would end up being the same after it's truncated. Okay, and so this is 1, 2, 3, 4, 5 times 4 times 3, 15, 30, 60, 10-digit numbers. So it's 10 to the power of 60. So that's a pretty big key. Let's see how many bits that is. I'll just write 60 10-digit numbers. All right, so 10 to the 60 is about 2 to the 200. So that's a huge number. It's like a cryptographic key kind of thing. In fact, that's hardly any compression at all. Maybe it might actually be uncompressed. Maybe they don't truncate it. I don't know what crypto that they're using, but generally G to the AB. Oh no, sorry. Yeah, it would be much bigger than this, because the exponents would be about 256 bits each, but the other thing would be bigger. It'd be like a point on an elliptic curve or whatever. But anyways, you're not going to guess it. So even if the adversary was trying to b-value, see if it matches, trying to b-value, see if it matches, you're never going to be able to do this many attempts. Okay, and then the third thing the adversary will do, that Alice will do, is she'll choose an ephemeral key. So we'll call it A0. So this is her session Diffie-Hellman exponent. And what she can do is send that to Bob. So she'll send her long-term secret, so Bob has it whenever he comes back online. She'll send her new ephemeral, and she'll sign the ephemeral with her long-term secret. And she'll send it to Bob. But because Bob is offline, there might be a server or something that collects it in the meantime. It might be the same server here. I drew them slightly different, but it will sort of collect it, hold on to it. Bob will eventually come online, and then he'll have G to the A, G to the A0, and the signature on it. And so Bob will also be able to derive the same safety number. He can take the G to the A that he received. He can raise it to his long-term secret, which is B, and then he's able to get the same safety number to compare. Okay. All right, questions about the first step here?
Wouldn't this also be the what's that sign?
The tilde? So what we're doing is the tilde is what's stored in the server. Because Alice is initiating the conversation and she's talking to Bob, she's going to use Bob's daily key. But if Bob was talking to Alice, he would use Alice's daily key. But because Alice is talking to Bob and Alice is online right now, she can generate a fresh key. She doesn't have to use her daily key. So the daily keys are just sort of like, they're offline keys. Let me write that. So you only use them when the other party is offline. If both parties are online at the same time, you could just go directly to ephemeral keys and long-term keys. You could skip this step.
But then in this step, Bob is offline.
Yeah, so Bob's offline, so that's why Bob's tilde is showing up. But Alice is not offline, so that's why her tilde is not showing up. Does that make sense? Yeah, so we're using Bob's daily key, but we're not using Alice's daily key because Alice is online right now. Does that make sense? Okay. All right, other questions about this? Okay, then when Bob comes back online, what both of them can do is they can both compute they can do a Diffie-Hellman between them. Now we have a couple things. We have G to the B, G to the B tilde, G to the A, G to the A0. Okay, so what are we doing a Diffie-Hellman with? What are the exponents? And so what Signal does is it does a three-way Diffie-Hellman. So it's going to do a Diffie-Hellman between G to Alice's long-term secret and Bob's daily, between Alice's ephemeral secret and Bob's long-term secret, and then between Alice's ephemeral and Bob's epoch key or session key, or it's not session key, is epoch key or daily key. Okay, and so those are the three things that we put together, and so it just sort of binds all of those things together. Okay, so what comes out of here is going to be dependent on Bob's long-term key as well as his daily key and Alice's long-term key and Alice's session key, essentially. Okay, so we mix all of them together, and then we're going to get out a master secret, and then we're going to turn around and we're going to use that master secret to set up a ratchet system that we'll use to send messages back and forth. Okay, so this is the handshake phase. So the handshake phase gets us to this point. Okay, so this can be done by both Alice and Bob. Bob, once he's online and sees the messages, he can do this as well. Okay, any questions about the handshake? Yeah.
Let me ask you this question first. Is the process different when it's like a group chat? Like would it
Yeah.
be for each person in the group chat?
Yeah, so the group chat is, Signal has a bunch of like more complicated protocols. So I'll just tell you like what they are. Well, there's basically three. So there's group chat. There's something happened to a message in the middle. I didn't get it, or I got the messages out of order kind of thing. I guess that's the same thing. So either messages got dropped or they got compromised somehow. So I got the wrong one. And so it's going to have like more complicated mechanisms for those three cases itself. So what I'm showing you right now is just between A and B themselves. In a group chat, if I recall correctly, there is a group key as opposed to pairwise keys between all the members of the groups. I think they derive an actual group key and they use it. But I have to double check that to be 100% sure. Yeah. Okay, other questions? Yep.
So you use elliptic curves like twice?
Yeah, so Diffie-Hellman is a protocol, and it requires some group. You run it over some math where the discrete logarithm problem is hard. Yeah. The groups where discrete logarithms are hard are usually one of two types. One is the integers mod a prime number, and the other is elliptic curve group. Why would you choose one over the other? Well, elliptic curves are a lot smaller. So for the same level of security, you get like way smaller things. And so all modern cryptography uses elliptic curves. Everything from TLS to Signal to Tor to Bitcoin, Ethereum, all that stuff. Yeah. And so anytime you see G here, I'm skipping it because you all either have or will take 6110. So I don't want to repeat too much of it. But G here is an element of a group where the discrete logarithm is hard. Yeah. So all of these are points on an elliptic curve. The output of the signature will be a set of points, a couple points on an elliptic curve. Yeah. So every time you see G to the something, that is a different point on a curve.
So like the initial handshake and the continuation of the chat.
Yeah. So anytime you do Diffie-Hellman and you have G to the something, that's using elliptic curves. Yeah. And the output, like G to the A, if you write down what that looks like you're going to pick a number for G, and you're going to pick a value for G, you're going to pick a value for A. The value of G will be an elliptic curve point. The value of A will be an integer. And then an integer scalar multiplied by an elliptic curve point will be an elliptic curve point. Does that make sense? Yeah. Okay. So those details you don't need to know for this course, but just for your interest.
The ratchet is being done on 3 different.
So this isn't a ratchet per se. I mean, I don't know. It depends how you define ratchet. So I define it loosely as, when you mix keying stuff together. But it's not this kind of ratchet yet. But we just call this a 3-way Diffie-Hellman. Yeah. But it is kind of a ratchet in the sense that you're mixing some different key materials together. Yeah. Okay, other questions? Okay, it's a good time for a break. So let's take a break and then we'll go through the protocol itself. Okay, questions about anything up to this point? No? Okay, we won't be too long. I'm probably not going to go through email. We'll just try and wrap up the Signal stuff and then we'll save email for after the break. Okay, so we have a shared key now between using the different ephemerals. And what I'm going to do is I'm going to use this key to set up a couple keys. Okay, so I'm going to choose a root key, and I'm going to use a key, I'm going to call it a chain key, CK, and it's going to be for sending from Alice to Bob. So this is chain key, and the S here means it's for sending, which means it's for Alice to Bob. And then when Bob responds, we'll set up a key for him to respond with. And we're going to call this a root key. Okay, I'm going to draw a big diagram. And this diagram is Alice's view of what's going on. And Bob will be able to derive all the same stuff, but I'm going to write it. So when I say sender, I mean Alice's view as a sender. In Bob's view, he'll be the sender, not the recipient, but everything should be recoverable from both. Okay, so we're going to have 4 kind of streams. We're going to have some Diffie-Hellman exponents. We're going to have our ratchet, which I'm going to call a root. So this will be a ratchet. And then I'm going to have a second ratchet, well, a second and a third, one for send. So these are messages from Alice to Bob, and one for receive. So messages from Bob back to Alice. And so these will also be a ratchet, but it will be a simpler ratchet than this one. So this ratchet will be exactly the ratchet that we derived up here. And this one will be kind of a ratchet, but it'll be a little simpler. So because there's 2 kinds of ratchets, we call it a double ratchet. So you'll see double ratchet all the time. If you go into Signal and try and read about its protocol, they'll say, oh, it uses a double ratchet. But you could also look at it as a triple ratchet because there's three ratchets, but 2 kinds of ratchets. So they tend to call it a double ratchet instead of a triple ratchet. Okay. So because I did this KDF, I have an RK0. So I'm going to start with that as my root key. And I have a CK zero. So a chain key, my first chain key, and I'm using it just to send. Okay. I'm not going to do anything with my root key until I hear back from Bob. When I hear back from Bob, I'm going to get his exponent, and then I'm going to update my root key. But for now, I'm just going to, this is Alice. She's just going to send messages to Bob. Okay. So what she's going to do is she's going to take her key and say, I'm about to send a message. I'm going to do one thing before I send a message. I'm going to get a key that's only for that message itself. So I'm going to run KDF on it. I'm not going to take a second input. So that's why it's a simpler ratchet. I'm just going to take my one input, and I'm going to get out a new chain key. And I'm going to get out a key that I can use to send. I'll call it S for sending key. So this is a send key. Use for first message only. So Alice sends, hi Bob. This is the key that's going to be used, S1. And it's going to be an encryption key. So it's going to be an encryption under S1 of whatever the first message is that we send. Okay. And this, as always, is going to be authenticated encryption. So it will encrypt and MAC at the same time. Okay. So I have S1. I use it to send that first message. Now let's say I'm going to send Bob a couple messages. Like I say, hi, enter. It sends as a message. And then I say, how are you, enter. So I'm sending 3 or 4 messages all at once. I'm going to use a different key for every single message. Okay, every message has its own key. So what I'm going to do is, if I want to send a second message, I'm just going to repeat the ratchet. I'll get CK2 and S2. Okay. And then let's say I want to send a third message. Okay.
Where is key stored?
Pardon me?
Where are the keys stored?
Which
Like
keys?
all these keys you're generating.
Okay, so good question. So first off, where is any one single key stored? It's on your phone or whatever. So it's going to be stored in my phone. If I'm done talking to Bob today, I'll remember my keys from when I talked to him. Okay, so I'm going to remember those keys, and then when I'm ready to pick the conversation up, I'll have the keys. Okay. Now the next question, you said, where are all these keys stored? Like the implication was, I'm going to have to store all of these keys, right? So this is what I want to think about next, which is which keys do I actually need? Okay, so once I send a message to Bob using S1 and I update my chain key and I have a new S2, am I ever going to need this key again? The answer is no. Okay, so what I'm going to do is I'm always going to keep, so let's say I'm done. I send my 3 messages. Let me pencil in a little more of the protocol and then I'll take care of this. So I'm going to encrypt with S2, message 2. I'll encrypt with S3, message 3. Okay, I'm done for a while now. Okay.
So this is when, sort of trying to picture it in my mind, you receive on your app that, let's say, like, there's a check mark that said that it was sent, the message, and then it sort of like highlights when the person views the message.
So this,
So once it views it, then you don't need the key.
so the view is a different protocol itself. Yeah, so the view would be when Bob looks at it, he would send a message back to Alice saying that he looked at it.
Okay.
But right now, this is like what I'm describing is the most basic version of Signal, which is just getting the message from Alice to Bob and back. None of the fancier features. Yeah? Okay. All right. I just sent message 3. Okay. Do I need S3? Do I need to remember S3?
Yes.
Why?
You need the latest one.
But why do I need S3? I just sent a message with it.
When you want to make the connection again,
Yeah.
you need it to basically to update whatever.
But do I? So that's the right intuition. So let's say I connect again. Now I'm ready to send message 4.
At that point,
I'm going to use K4.
you don't.
So do I need S3 to get it? I don't, right? I just need CK3. Yeah, okay. So I do not need this anymore. Once I send the message, I don't need it. I need this. And if I need this, I can continue the chain. And I can derive future keys. Do I need these keys, my previous keys? No. Okay, so I can forget these keys. Doesn't matter. I can forget these keys. I can forget these keys. I can forget this key. The root key, we haven't seen what we're using it for, but we will store it. Okay, so at any time, I'm just remembering 2 keys for now. When Bob starts sending me messages back, I'll remember his key as well. Okay, so at all times, I'll have 3 keys. I'll have my root key. I'll have my latest key that I use to derive a send key, and the latest chain key for receiving keys. Okay, and those are the 3 things. All right. We said that ratchets have 3 properties: forward secrecy, break-in recovery, and resilience. This is a simpler ratchet, okay? So do we have all 3 of those properties or not? So let's go through them one by one. Do we have forward secrecy? So let's say I compromise S2. Can you go back and get S1?
No.
You cannot, okay? So this is right here, let me do it in pink. So it's a simpler ratchet. So forward secrecy, I have that property. What about break-in recovery? So let's say that you steal CK1. Can you figure out CK2, CK3, S2, and S3? But where's the Diffie-Hellman?
The Diffie-Hellman actually comes into the KDF.
Okay. So when I said it's a simpler ratchet, what I meant is that there is no Diffie-Hellman. So that is true about this. So the complex ratchet is it takes two inputs and gives two outputs. And so by simple ratchet here, I mean it just has one input. One input, no Diffie-Hellman.
But still, you don't know the how about of the KDF.
KDF is a public function. It's a hash function, a PRG, or something like that. Yeah.
And since it's a hash function, so you can actually do the.
So it's one way you can't go backwards, but can you go forward?
Is it random?
So there's no the key in KDF is just this key here.
But you still can't go backwards.
You cannot go backwards. Yeah, that's correct. So, but here we're talking about if I compromise S2, can I get S3? So can I go forward, down?
If you know S2, no.
Okay, so if I know just S2, I can't go forward because I would have to get the CK. What if I get the chain key?
But it's still not S2.
I don't, do I need S2? What is,
Right?
these only depend on CK2, right? That
I'm testing it to
would just say I can't find two different inputs that produce the same output. Okay, so the answer is I can go forward. Okay, so if I get CK2, then I can compute CK3, I can compute S3, and I can keep going all the way down. Okay, so it does not have break-in recovery for the CK. So break-in for CK. It does have break-in for the S's. So if for some reason I can get the S key, then I could protect everything. But if I get this chain key, then I'm done. Okay. So this is why we're going to want to get the Diffie-Hellman into this somehow. Okay. But in order to do that, we need Bob because I need Bob's exponent. So right now I just know mine. Okay. So, but anyways, within one sort of set of messages that I send, there is no break-in recovery, okay? When Bob responds, then we're going to do something so that it protects the next kind of chunk of messages, okay? So messages kind of go into chunks. So I send a chunk of messages, get a chunk back, I send you a chunk, and within each chunk, there isn't break-in recovery if you recover the chain key, but across chunks there will be, okay? So we'll get there in a second, okay? But that's why this ratchet is simpler. And then there's really no notion of resilience because we don't have any side values going into it. So it's sort of like, it's kind of like, I'll write NA for like not applicable. For resilience. Okay, so this is the simpler ratchet itself. Okay, everyone good so far? Okay,
Yeah.
Now we hear back from Bob. And what Bob is going to do is he's going to send a new Diffie-Hellman. So I'll just say that Alice is on her original A0. What Bob is going to do is going to send a new B1. Okay, so Bob to Alice we'll send a new G to the B1. Okay. Now we can update our shared secret. So now we have A0B1 instead of A0B0. Okay. And what we can do is we can ratchet using a proper ratchet. And that will give us a new root key. And what we'll do is we'll use this to give us a new chain key for receiving messages from Bob. And we can start the counter wherever. I'll start it at 0 again. Okay. And then now Bob wants to send a message. So he does the same thing. He does a simple ratchet. So he does KDF. He updates the chain key. And he gets a send or a receive key. So this is the key that's used for sending messages from Bob to Alice. So Bob to Alice will use this key. He'll encrypt under R1 his message back. Okay. Then we'll continue. So let's say he wants to send 2 messages to us. Then he'll keep doing this. Okay. Once I get his second message, I don't have to remember these R's anymore. What I'm going to do is, again, this is Alice's view of the protocol. So after we've ratcheted, I don't need K0 anymore. Okay. So all I need is, I should have updated that, sorry, to K1. So I'm going to keep this in memory. Okay. I don't need to remember this anymore. And I'm going to keep this in memory. And once I've decrypted this, I don't need it anymore. And I don't need any of these previous keys. Okay. So at this point, I've got some messages back from Bob. I still know my latest send chain key. I know where the root key's at. And I know where the receiving key's at. Okay. And I actually misspoke. I guess technically you can forget these 2 chain keys. What you'll do is you'll always refresh the chain keys from the root key. So you actually don't have to remember these anymore. But anyways, I'll just leave it. It's sort of complicated. If say I didn't hear back from Bob, and then like I sent him a bunch of messages today, and then I didn't hear back from him, and then I want to send him a couple more, like a reminder, then I would need K3 to continue this conversation. But once I hear back from Bob, I'm not going to use, okay, let me put it this way. Once I hear back from Bob, I can forget this key for now, okay? Because I know that the next time I send a message to Bob, I'm going to update my own key with this, okay? So next time I'm ready to send messages back, I can update my Diffie-Hellman now. So I'll do this from A1 to B1. So I'll get out RK2. I'll update my root key. And then what I'll do is I'll create a new chain key for sending. I'll label it as 4 because that's where I was at before. Okay. And then I repeat the process. So if I want to send a message, I get a key for that message. We'll call it S4. So this is my 4th message that I'm sending. And now the numbers are sort of out of whack, but that's okay. I'll call this 5. Okay. And then I use this to send a message to Bob. Okay, now let's say that, I don't know, CK2 is compromised. Okay, so the adversary gets CK2. We have established that the adversary can get CK3. Okay? But once I go back here and refresh here, and now I get CK4, the adversary doesn't know G to the A B1. They also don't know G to the A0 B1. And so they aren't able to, so basically they can, as long as I keep sending messages within the same sort of time slot, they can recover all the future messages. But once the conversation switches and we ratchet, so the term ratchet means we do this Diffie-Hellman thing, then we get a whole new root key, and we're going to use that root key to derive a whole new chain key. Okay, so the old chain key doesn't matter anymore. All right, and so then we can continue onwards. Okay, so
every conversation it does this?
yeah, so roughly every message you send will be encrypted with a unique key.
Yeah.
And every time the conversation does a round trip, then we'll ratchet and create a new kind of key. Okay, so yeah.
WhatsApp and Signal both do this.
Yes, yeah,
Okay.
that's right, yeah.
But Signal is just a bit more private.
Yeah, so Signal hides a lot of the kind of the meta information as well, like who's talking to who, or if there's a group chat, who's in the group,
Oh.
that kind of stuff. Whereas WhatsApp, owned by Facebook, likes
They
that
keep
kind of
that
stuff.
information.
Yeah.
Also, like something like Telegram, the company actually has the decryption key, so theoretically they can actually access them if they are not being like ethical.
Yeah.
But in Signal, no one sent the recipient yet.
But WhatsApp, do they store all the conversations?
The
and
problem
everything?
with WhatsApp is the metadata.
Just that?
They store the metadata.
But not the actual message.
Yeah, so you do have an end-to-end key between Alice and Bob. And so what Telegram, I believe, does is they don't give you a way to check the long-term key itself. And so when they give you an ephemeral key, I don't know if it's strictly necessary that they are in the middle, but they, at least in theory, could be in the middle. So when you get this key, you don't know whether it's actually Bob's key or it's a key that the server made up for Bob
The
itself.
decryption key is basically with Bob and the owner of the company. So like they both can decrypt.
I see.
That's what they claim, that it's secure, like you can chat anything.
For Telegram?
Yeah.
Okay.
That's what they claim that it's.
Yeah. So I know Telegram isn't actually properly end-to-end secure.
Yeah.
So they claim a lot in terms of security that they don't achieve.
Yeah, because they
But-
don't know.
Yeah.
Because in the meta they have the proof that what the information they get, what information can be seen, who see what. But the Telegram, they actually they claim that they are secure. You can share, send the chat and everything. Nobody's watching, nobody's saving anything. But it's actually not true.
Yeah, okay. Yeah, so the server in the middle either has the ability to impersonate users or in the extreme case would actually know, it's maybe creating the keys for you, giving you a copy of it, and then it has a key in the middle. Yeah.
The thing about Telegram is that the owner is a very anarchist, so I don't know if you recall, but they had this whole court thing about like Paul Moore
Yeah.
when he didn't actually give out the data.
Yeah, exactly.
So yeah, it's not about like it being secure, it's about him being like safeguarding the data.
Yeah. But that's what the case was with the metadata. They said that they don't keep it, but they keep data. That's why the case
So
of
they
Telegram said that they don't, that he didn't even reveal everything.
Yeah, they don't reveal
Yeah.
it, but they actually have it because like everything is on it's stored on the cloud
Yeah.
for Telegram. Like unlike WhatsApp, which is like the cache is cleared like every 30 days. In Telegram, you can actually access the like a video you uploaded like 2 years ago.
Yeah, exactly.
Yeah.
But sir, isn't WhatsApp end-to-end, so they're supposed not to see anything, right?
Yeah, so if to the extent that they use is, so a lot of
When
this,
they receive it.
yeah. So they do have end-to-end encryption, my understanding. They use Signal properly, so they have end-to-end encryption. But a lot of it actually comes down to the safety number, and a lot of people aren't going to check that. Like all the friends I have on Signal, like we've never actually sat together and checked our safety numbers. And so if you don't check it, I mean, technically they would get caught if they were messing with it. But anyways, the other thing too, I mean, you can also argue, well, it's a user interface. So maybe the crypto keys that are being used and what the user interface is showing you isn't the same anyways. So because they're designing the app itself, if Signal went bad, there is ways, or WhatsApp went bad, there's ways that they could trick you anyways, because you don't really know whether this actually matches the keys that are being used under the.
So at the end of the day, you're actually trusting the centralization of the.
Yeah, exactly. Yeah. And that's generally true anyways. Like even if I run something through an encryption algorithm, it could not do the encryption right or deliberately do it slightly wrong or things like that. So, in general, you always sort of you end up trusting the apps themselves that they're implemented correctly and things like that.
Voice is the same.
Yeah, so the voice, I understand that the way that it sets up keys is the same. And so this could be like a channel, an audio channel from A to B. I don't know how often they
Instead of the
refresh it.
text, it's just the audio.
Yeah, so the key stuff is the same, but obviously it's more complicated in terms of the data that's being sent. Yeah.
You mentioned before that the server has to be trusted. Could you explain why?
So the server, the safety number is what makes, so it's trusted until you verify the safety number. So if I don't check the safety number, then I can just trust that the server is not lying about, basically the only thing it can lie about is the long-term keys. And with the safety number, I'm checking that what you think is my long-term key and what I think is your long-term key is right, that they match. Again, trusting that the software apps are correctly coded. Yeah. So that's what makes the server untrusted. But the reason why it's also not so dangerous to use Signal with someone, even if we don't check the safety numbers, is because the servers are probably trustworthy. Yeah. But technically you would want to verify that.
I never even knew that existed until now.
Yeah.
Nobody probably knows that.
Correct. Yeah. So they've gone back and forth on like, should they promote it or not promote it? There's also Signal's like kind of in a long chain of secure messaging protocols. And so other messaging protocols like OTR was like the original off the record messaging. I think it's more in your face, if I remember correctly, about like getting you to try and check these fingerprints.
Yeah.
But in Signal and WhatsApp, they just sort of buried it. And even in WhatsApp, I know when they first turned on Signal, you couldn't do this. And so then people are saying, well, it's not truly end-to-end secure because you have no way of doing this. And then I actually don't, because I don't use it, I'm not sure. I don't know what they do in terms of this. They might actually do nothing. I don't know. I just know in Signal you can check it. But, yeah. Okay. So let me just take some notes about the security here. So resilience, we have that property. Forward secrecy, we basically have this for all keys. So regardless of what keys you're stealing, you're not going to be able to see future round keys. You're not going to be able to go back to the previous key. Basically, every time you're going to hit a KDF and you're not going to get the key on the other side of it. Break-in recovery is a little more complicated. So it depends on what you're stealing. So let's just sort of break it down. So if I steal the send and receive keys, then it's fine. There's no problem. If I steal the chain keys, either on the send or on the receive, I don't have it until we do another Diffie-Hellman ratchet. And then after, I do have it again. Okay, so I until something happens here, I can break all future messages. But then once something happens here, then I can't do it. How often does something happen here? Well, basically every time the conversation flips from one person to another. So in other words, if I send 10 messages to you all in one bundle, and you're able to seal the key, say for the first one, you can read all 10 of those messages, but then you're going to lose track after that. Okay. And then if I steal the RKs, or even in the extreme example, if I steal your long-term key. So let's say I choose steal G to the A or G to the B. Then I can't actually read your conversations. Okay? So if I get your root secret key, say I get it off the device, whatever conversations you've started and you've already ratcheted at least once, I'm not going to be able to read those. Okay? However, it's sort of a more complicated thing. If I steal GA and I'll say after ratcheting, if I steal GA from you, though, I can impersonate you in the future. So anyone that you've not started a conversation with and they want to talk to you for the first time, now I can impersonate you and I can get everything. So you'll do a Diffie-Hellman handshake with me, right? So well, what I'll do is I'll go back to the server. Now I know your long-term secret. So I'll create a bunch of epoch keys where I know the secrets. Then we'll do Diffie-Hellman. I know the secret and I chose the epoch key, so I'm going to be able to derive these keys. And once I derive these keys, every time you send me a new Diffie-Hellman, I know the other half of it. And so it's over at that point. Okay? So GA is not secure for new conversations. And that kind of makes sense. I mean, if I can steal your long-term identity, I am you at that point, right? So any conversation someone tries to have with you, they could be having it with me instead because I am you. There's now nothing in the world that separates me from you. I know everything that you know and things like that. Okay? But if you've already ratcheted a couple times or even just once, and then I steal your long-term key, then I won't be able to break into the communication. Okay, so
You never talk to ever. Like, if there's already a conversation history, then that won't work, right?
yeah, so once Alice, remember she forgets,
Oh, yeah.
she starts forgetting her pass keys.
Yes.
And so once she's, for example, here and has this key, that's the only thing she's going to remember. And you can't get this, you can't go from here to here without knowing this stuff, kind of thing. Yeah. Okay, other questions? Okay, there's one other property I want to talk about that's not covered here. So anything about the protocol itself? Okay. So Signal also has a property that a bunch of secure messaging has, and even HTTPS has it as well, called deniability. So let's say that Alice sends to Bob some sort of message. And Bob writes down everything about the message. He writes down all the keys that were used, all the signatures. Basically, he draws out this whole entire tree. Okay? And then what he does is he shows that to someone else. He says, look at the message that Alice sent to me. Here's the message, and here's all these crypto keys, and you can sort of backtrace them to signatures and Alice's long-term key and all that stuff. Does that cryptographically prove that Alice sent that message or not? Okay, so Bob shows message and all keys to Carol. Does it prove that Alice sent that message? Okay, any guesses?
I think no.
I wanna say no, but I don't
No.
know why.
Okay.
Bob can forge the message himself because he has all the required keys.
Okay, so let's start with that. Bob can forge the message because he has all the required keys. Let's zero on that word forge. What does forge mean?
Like, you
Change.
could say that I sent the message instead of Alice.
Yeah, that agreed. Okay, so we can change either the contents of the message or we can change the direction of the message. What stops a forgery?
Signature.
Yeah, okay, so signatures. Let me ask a related question first.
The Mac.
Or a Mac. Okay, so we have signatures or Macs. Okay, let me ask a related question. Let's say let's say Bob just gets the message from Alice. Does Bob know that that's the message that Alice sent? Is Bob himself convinced of that?
I mean, Bob is in the chat with Alice, so and
Yeah.
so he knows that it's between him and Alice.
Okay, so let's pencil that in. Okay, so Bob knows Alice sent the message. If he didn't, then we wouldn't have message integrity. Okay, that's one of the basic properties that we want. Okay, so Bob knows Alice sent the message. So that's message integrity. And now the question is how? What crypto primitive gives message integrity? So there's two. It's either a signature. So Alice could sign the message, say with her long-term key. Okay? Then I would say, yes, Alice sent it. No one in the middle modified it. Or Alice could MAC the message with a shared key that I have with Alice. Then I know that no one, I know I didn't modify it, and Alice is the only one that knows that key besides me. So therefore, Alice must have sent it.
But with signatures, it's more accurate because it provides non-repudiation, right?
Okay, so signatures seem stronger, right? So let's think about Alice signs the message versus Alice MACs a message.
Mac is just gonna tell you if it's changed or not. The signature is gonna tell you that it came from.
From the specific person.
Yeah.
Okay, so a signature is transferable. So I can show it to someone else, and they'll believe that if they know that this is Alice's key, right? So if G to the A is Alice's public key, then sig is, we'll say, undeniable, non-reputable, undeniable. There's a couple of words that are thrown around in crypto things. But yeah, basically it proves that Alice sent this message. She's the only one that could send it because she's the only one that knows A. Okay. Now, if she MACs it instead, okay, does anyone else know A?
Yes.
Who?
I think
Okay. So how do you verify a MAC? You recompute it, right? So I get a message, it's MACed. I have to recompute the MAC on the message and see if they match. I need the key as well. Okay. So A is now a shared key. Is shared between Alice and Bob. So how does Bob know that the message is right? Well, he knows he didn't, either Alice made this message or Bob made the message. I know I didn't make the message, so it must have been Alice. Okay, so that's the reasoning. So the MAC doesn't prove that Alice made the message. It just proves either Alice or Bob made the message. But because Bob knows himself, and he knows that he didn't make it, then it must have been Alice. Okay? Now, what if Bob goes and shows it to Carol? Says, here's a message and here's a MAC on the message.
It's not important.
Yeah, so Carol is like, well, you know the key, and Alice also knows the key. So I actually have no clue whether you made the message up and saying it's something that Alice sent to you, or if Alice actually sent it.
Because he
Yeah.
doesn't know.
Because the key is shared between two people, he doesn't know who created the message. He knows it was either Alice or Bob, or Carol. Oh, it's either Alice or Bob, but she doesn't know which. So if Bob's trying to convince Carol about something Alice said, Bob could just make up stuff. He could MAC it because he knows the key, and then say, "Oh, Alice sent it." Yeah. Okay. So so it ends up being deniable. Okay, so Bob can't show a MAC and have it prove anything. Even if you prove that this A traces back to Alice's long-term secret, that's fine. That just proves that that it was a key between Alice and Bob. Like Alice was one of the people that know the key, but she wasn't the only person that knows the key. Okay.
What do you mean here by deniable on the Mac part?
Deniable means that Alice can. So when Bob shows the message to Carol, Alice can say, "Oh, I didn't send that."
That's deniable.
That's deniable. Yeah. Okay. Even with messages she did send, right?
Okay.
So I can send a bunch of messages to Bob, and it's true I sent them. But if Bob tries to show Carol, I'll just be like, "Oh no, you made that up," and there's no crypto evidence either way.
On the other hand, if it's signed, she can't.
If it's signed, then you can't deny it. Yeah. Yeah. Assuming that your key wasn't stolen or something like that. Yeah.
With the double ratchet must have moved forward so that we have the previous MAC.
Okay, so where is the MAC key in this ratchet system?
So the MACs are the keys that we get.
Okay, so the MAC is inherent. So we said authenticated encryption here. That's basically encryption plus a MAC. And so, and it might be a MAC that's sort of built into the mode of operation, or it might be a separate one. It doesn't matter for the purposes of this. So that's where this is coming from. So first off, which of these two worlds are we using in Signal? So we're using this. This is what we're using in Signal. So Signal is using this for every message when it does encrypt with, say, S or R of a message. And this is authenticated encryption, meaning there's a MAC. Sorry, say again.
Is it like OTR?
Yeah, so OTR is sort of a predecessor to Signal. It also does a Diffie-Hellman kind of thing where you set up session keys, and then you are able to, at the end of the day, you just MAC things instead of signing them itself. Okay, this is going to be in contrast to email. So in email, what's going to happen is we're going to have signatures on things if we have any message integrity. So there's a lot of cases where we have no message integrity, but when we do, it's actually someone's directly signing it. Okay, so if you send an email, you can't really deny it after the fact. We've seen this like in the news. For example, a politician in the US, Hillary Clinton, had an email server that was hacked and all the emails got dumped, right? And so you could check if you do, you would have to have a binding between the key and either her or her email provider, but you could go and you could check those things, okay? Recently, Jeffrey Epstein has a bunch of emails. As far as I know, they didn't release the headers of those files, so you can't check whatever signatures may have been in place there or not, as far as I know. But in theory, you could check it if you were worried about like some of those being made up. So it's not deniable, yeah. So you can prove, if you sign it with a key that everyone knows is your key, yeah.
In email.
In email, if you send an email with a key, so it's hard to send a signed email. We're going to learn that when we talk about email. You need to use something beyond email itself. So you're either going to use something called PGP, or you're going to use something called SMIME. There's a couple others. Or you might use like Proton Mail or like a couple like webmail services that build that stuff in, but only when you're emailing other Proton Mail users, not when you're sending email out. But anyways, in these cases, yeah, you're going to sign things directly, and you're not going to be able to deny them at the end. If you use normal email,
There's your IP address that you send email from is you can look that up in the email.
yep. So the email protocol will include the sender's IP address. It's part of one of the fields that gets included.
Can prove unless you use a VPN.
Yeah, so it could trace the email back to the originating IP address. Yeah. But anyways, okay. So we have deniability here because we're using authenticated encryption. The encryption uses a MAC, and because we're not signing things directly, we're using a MAC. Then Bob knows Alice sent the message, so that's true. But because it's a MAC, he can't show that to someone else. So Bob knows it's true for himself, but he can't transfer that knowledge or that proof to someone else. So it's non-transferable evidence or deniable. So this is another feature. Now, in real life, I mean, there have been cases of conversations that have happened over OTR or over Signal, and there's been court cases. And even though technically you could deny it, you know, people take screenshots, or if there's a server in the middle and it kind of listens, it can kind of timestamp when certain messages are sent and what IP address it went from others. You can build a lot of circumstantial evidence that someone sent this message. So even though it's cryptographically deniable, the best way to think about it is it doesn't give any more evidence than if you didn't use cryptography at all. So if I just send you a message unencrypted, you could still try to prove I sent that message to you with a screenshot or a server that's in the middle listening or whatever, right? There's just not like strong cryptographic evidence because there's no cryptography. So here, deniable just means it reduces to as if you send it without cryptography. Whereas here, if you sign something, then deniability, you can't deny it. There's strong cryptographic evidence. So it's worse than not signing it at all, kind of. So anyway, so deniability is sort of a complicated thing when it comes to like using it in practice. Like most people don't go around like denying things that were sent. But anyways, it technically is one of the features of Signal and coming from OTR. And it also applies, by the way, to TLS.
I have a question.
Yeah.
So what's the main difference between Signals and WhatsApp?
So WhatsApp uses Signal. So WhatsApp's cryptography uses Signal itself. So Signal's an open source protocol, so anyone can use it.
Okay.
It's the same way.
The app, I mean the app.
Oh, the app itself? It's just, so the crypto is the same underneath, but then like the features of the app, how you find friends.
Cryptographic.
Yeah, so at a cryptographic level, they're identical except for, like I say, I'm not sure about how WhatsApp handles the safety number thing.
Let me see.
Yeah, and so that's it.
Tokens, they're the same mainly.
Yeah, so they both have end-to-end encryption. But then there's a bunch of information that you're sending to, like, what IP sent this to which IP, or which user sent it to what time did they send it? Let's say you have a group chat with 10 people in it. Who are the 10 people in the group chat? That's not,
More private.
yeah, that's not being encrypted. So we call that metadata. So metadata is the data that's outside of the encryption. It's the stuff that's written on the outside of the envelope.
Okay.
Yeah. And so there are differences in terms of WhatsApp collecting, remembering the metadata more than Signal does itself. But
On WhatsApp, they have something called verified encryption between you and a contact, and then you can compare the 60 numbers.
okay, cool. Yeah. So it has the exact same safety number thing.
It's just different.
Yeah. So essentially, the cryptography is the same. Some of the stuff around the cryptography is different between the two, and so generally people say that Signal's more private than WhatsApp, but they don't mean that at cryptographic level.
Metadata, right?
They mean it for metadata. Yeah.
Because it's open source Signal app, right?
Yeah.
It's an open source.
Yeah.
Text messages also traceable now?
So SMS, so it depends. So what keeps this? So this is actually sort of the connection between this and email. So Signal's a closed system. So I'm talking to you on Signal. We both have the app installed, correct? For SMS, I just need a phone number. I don't need a special app or something like that. So if I want to send a SMS to you and you have a phone number, I have no idea whether you can do encryption or not. So SMS itself, the SMS protocol doesn't have any encryption
Like on
built
an
into it.
older phone or something like that, that doesn't, like not a smartphone.
Even the SMS right now, right?
So because I need to be able to send an SMS to any phone number,
Yeah.
and all I know is that person has a phone, not necessarily a smartphone or anything, I can't make any assumptions about what cryptography they can use.
So it's less
Yeah.
secure, right?
So it's less secure. There is no encryption on SMS
At all?
until, for example, let's say I'm on an iPhone and somehow my iPhone figures out you're on an iPhone as well. Now we're in a closed system. So it's Apple to Apple. And so Apple's going to switch me from SMS to iMessage. And when it makes that switch, then it's going to put end-to-end encryption on it for
It
us.
has to both be Apple.
Yeah, so once both are Apple, then you can do you can do iMessage, which is end-to-end encrypted. I believe on Android it's the same, Android to Android. And now there's like some stuff where Google wants to be able to receive iMessages and vice versa, so they're going to implement the same crypto protocols. So that if you're on Android, you can get an iMessage message. And I don't know all the little details of that, but yeah. And I'm also not sure if you can do this on iMessage. I haven't seen that interface. So I think you are kind of trusting Apple in the middle as a key server as well. Yeah, so I think it is end-to-end encrypted, but you're trusting the server to give you the right long-term keys
At the end
of
of the day, most
things.
people and trusting the server.
They cut in the
Yeah, exactly. Yeah. And at the end of the day, remember you're trusting their code anyways. So, if they want to mess it up, they have a million places where they can mess it up. Yeah.
Also, it depends on their policy also. If they have a policy that they're not gonna save this and that information, and they will never share the information to any public body. It could be government authorization also, which happened in like 2000s.
Yeah.
When there was an attack on United States and the attacker had iPhone. So they killed him, but they got the iPhone. It was 5S or something. And the government, US government, they wanted Apple to open the phone so they can see what was the conversation. Apple denied it.
Correct.
We will never open, it's not in our policy.
Yeah. So that's about like lock screens on phones, but that's correct. Like they had to hire like some firm and they were able to get into it eventually, but
It took
But-
3 years.
well, yeah, I forget exactly, but it had this feature where if you put the password in wrong
And
5
like
times, it
1
wipes.
hour, then it runs 24 hours.
Yeah.
Then in the end, it will just erase it.
Yeah. So they had to break it at the hardware level basically to get it out. What I think for iMessage 2, so Apple does promise to do it right, but there have been cases where governments, like I remember India, there was this something between India and I forget if it was WhatsApp or if it was iMessage, where they wanted some keys in the middle. And I think, I think Apple or WhatsApp, Facebook ended up complying with it. That's my memory. I don't remember the exact news story. So so there might be cases where you don't get end-to-end encryption.
They got with
But-
the TikTok also.
Okay. And was it to break the encryption or just to get the metadata?
They wanted to control the interaction for the user, that what information you can filter for the user in a country.
Yeah.
Same as China, we don't see the same information what they can control it. This is like control version of what you can do. That's only the way that the India will allow your application, which is for 1.4 billion people, you wanna use it. But then you have to apply with them.
Yeah. So anyways, governments can play tricks in the middle. Companies they try to maintain user privacy, but if you're going to cut off like an entire continent of people, then they might not.
So as far as we know, in Canada, they're not like law enforcement and all that, is live checking all the understand you do that.
Yeah, so as long as the safety number feature is in place,
They can't do it.
you have end-to-end encryption, assuming the code, like the software is coded correctly. So that's why they call it a safety number. So I assume that if there's any countries where things are getting broken in the middle, then this feature is also getting removed as well. And so users are sort of consenting to it. But yeah.
In Canada, if you're a government employee, you cannot install TikTok on your cell phone.
Yeah. So that's
On
for.
your work cell phone?
On your work cell phone.
So Concordia actually has the same policy.
Yeah.
So at Concordia, you're not allowed to install it on.
So if I wanna use it.
Not that Concordia gives out phones, but if they did, yeah.
Because it's a Chinese app?
Because it's
No, because
origins.
they did not apply the service the government wanted to impose, like you cannot get all the information of the person device, because when we use the TikTok, you might have not read it, you apply that they can access hardware internal information from your device.
The permissions are too.
Only TikTok?
Yes, TikTok do that.
So TikTok, probably not only TikTok, but it's one of the. It's the most popular Chinese app that would have that
The
permissions,
rules
but
are changing regarding TikTok though, because of the Oracle buyout.
yeah, right. Yeah, I know the U.S. is trying to get someone to buy them.
So if you have sensitive information, you're not gonna use TikTok.
Yes, yeah. Okay, other questions, comments?
For government employees, I cannot use
The
work
RCS,
cell.
rich chatting system that Android is trying to implement for iPhone as well, the green bubbles. iPhone is testing iMessage for MLS that RCS uses. MLS is messaging security messaging layer security.
I see.
And it might introduce an end-to-end encryption, but not right now.
I see. Cool. Okay. Anything else? Nope.
The exam, what
Yeah.
kind of questions they will be?
Okay, so first off, let me remind you before you all go. So next week is reading week, so no class. No office hours next week either. So I'll be out of country. And then we'll come back. We'll have one lecture, and then the midterm will be the following lecture itself. Questions? Okay, so I've never taught this course before. So normally I could tell you exactly what things look like because I have past exams. So I can't tell you based on past exams. I can tell you what I generally do based on other courses. I haven't written the midterm for this yet. So I try to ask conceptual questions, and I encourage you to try and understand everything that was taught. I like to give you like a new scenario that's related to something that we talked, but I won't necessarily tell you what the connection is. So it'll be like, I don't know, Alice and Bob want to do X, Y, Z. You know, should they do this, this, or this? And then it will be based on something, like it will be based on forward secrecy or something like that. And but you'll have to recognize that out of context.
But will it be like driven, like you have this and that kind of development, between this and that, and this is the KDT, you have to drive a chart or a application?
What I'll try really hard to just make it multiple choice.
Most of it?
Sorry?
All of it?
I'll try and make it 100% multiple choice. I'm not promising that. Maybe there'll be short answer questions. But if I wanted a chart or something, it wouldn't be like draw it out. It'd be more like, here it is partially drawn out. Like, what do you do next? Or is this right or is this wrong? Like, I'll turn it into kind of a multiple choice kind of thing. But the point is, like, why do I want it to draw out? It's because I want to know that you know something about how to draw it. So I'll just take that something that I want you to know and turn it into a different kind of question. So it'll still test you on that same concept, but it won't be explicitly about drawing. But
Would you be able to give us some like dummy questions before the exam?
no. So I don't have a previous exam, and I can't write 2 exams. It's hard enough to write 1. Yeah.
Is the next lecture going to be included in the midterms?
Perhaps ask me at next lecture. But I don't see the harm. It won't be. It might be like 1 question anyways, or something like that. But probably, yeah. Actually, you know what? Maybe let's say not. It's 6 weeks now. It's actually kind of a clean break. So let's do the first 6 weeks Yeah. So the next lecture we'll do on email, and it won't be on the exam. Yeah. So that was the same question. No, I don't have sample. I haven't taught the course before, and I don't want to create 2 exams. Yeah. Plus, I'll write it the day before anyway, so you won't get it. Even if I wrote 2 exams the day before, you would only have a day to study them, and you wouldn't have the answers or anything anyway. So.
Will it be a class before and after this exam go home?
So there will be nothing after the exam. So the exam will be 90 minutes. There'll be some people writing in the can't say that word, accessibility center. They have 90 minutes, so I can't. I have to be very strict. You know, if everyone's still writing at the end of 90 minutes, I have to take your exams because they'll be writing in the other center as well. And they're sorry. Yeah. Everything will be just in class, and yeah. So you'll come to class, you'll write. When you're done the exam, you go home. There won't be a lecture after.
What is that accessible?
So students that have, like, say, a learning disability, they might not want to write in a class that's, say, it's too loud, so they might use headphones so they can write in the other place. Sometimes you have an accommodation like you're allowed 25% more or 50% more time.
How you prove it?
That's, you can, so there's, I don't actually know what the whole process is itself, but that's not my, I don't get involved in that. I just, they tell me what to do and I do it. Yeah.
It will be in the class, right? Yeah, the same time.
Yeah. So we'll write it here. You'll just come to class. You'll write an exam. It'll be over in 90 minutes, and then that's it.
And how many questions is gonna be?
So if it's multiple choice, 90 minutes. I don't know. Like maybe. Let's say it's 5 minutes a question. Then that would be 6 plus 3. No, my math is wrong. That's 12 plus 6, right? 18?
5 minutes is question, it's 18.
18, yeah. So it might be something like 20 questions. 5 minutes is a little long, but like it wouldn't be like a minute a question or 2 minutes. It'd be like somewhere like around between 2 and 5. So think like 20, 25 questions. Okay, you're welcome. Yeah, see you, August.